Hello to everybody. I would like to welcome you to our first afternoon session. My name is Ehrenfried Czech from Dresden in Germany, and it's a great pleasure for me to announce our first speaker. It's Marcella Boncio from the Department of Chemistry of the University of Padua in Italy. Marcella, it's your floor.
Okay, so thank you very much for this invitation in this spectacular place, wonderful city and, community. So the slides today will focus on a project that is really close to our heart and deals with a new concept for artificial photosynthesis. And so in the picture here, you will see these are chloroplast membranes, okay, where our oxygen is evolved from water, the oxygen that we need to breathe for our life. And you will see these are hierarchical stacked membranes that also can move and align following the light. This is to maximize efficiency because the photocatalytic processes that nature deals with, so I was saying that the processes, and we will go into it, are very difficult, meaning they have a huge thermodynamic and kinetic gap, especially, dealing with oxygen evolution from water. So these are heroes here in our department because it's very difficult to get into this mechanism and into these devices. And so the work that I will present, it's theirs. So it's because of their dedication. Okay, so let's talk about all right, the artificial leaf, okay? Can we reproduce in a lab these processes, okay? That, of course, deals with a tandem photo electrocatalytic cell. This is the most mature technology right now, and basically means that we have, to use water as a renewable sources of protons and electrons, okay? We split the water here, and then we would use protons and electrons at the other photoredox compartment, reduction compartment, to produce, to recombine and produce hydrogen, and in this case it will be green hydrogen because made by renewable resources and visible light, okay? If we mimic the green plants, okay, or CO2 reduction into, different products. So basically solar fuels. Now, okay, so the first technology was developed in Japan, and this is the Honda Fujishima photoelectrocatalytic cell. You can see, it works with two electrodes. One is a photo anode based on titanium dioxide, and which is connected by wire to the reduction electrode, where we will have the recombination of protons and electrons, and in this case producing hydrogen. Okay, so the photoelectrochemical cell, this technology, is based on a division of task, okay? Water oxidation occurs at the anode, and the reduction part occurs in a separate electrode. But this is not what nature does. Nature is not dividing. Nature is making compartments, and if we look at the other way, okay, nature uses membrane, okay, to connect, to make a connection, okay, and regulation by cofactor. So it's a very complicated process, okay? And so our purpose here, okay, is to imitate nature, okay? And this is a scheme about, you know, the natural photosynthetic membrane where water oxidation occurs at the photosystem 2, PS2, okay? Here, water is cleaved in protons and electrons, so we have then an electron transport chain, and of course, we have the combination and the connection with the photosystem 1 to produce reactive hydrides, okay? And part of the story is, of course, this jewel of inorganic chemistry. This is the oxygen evolving center, and this is a tetranuclear, tetramanganese, polyoxo metallate, okay? So we have the connection through oxygen, okay? This is the core of the problem. So how is the morphology and geometry of photosystem 2, okay? If we look at the structure, and now we have data about that, it's a core shell geometry, okay? At the core, we have the unit that cleaves water into oxygen. At the peripheral shell, we have the antenna that collect light to power, you know, the reaction center, which is here, okay? And the membrane, you know, is pretty well organized, okay? It depends on the condition of light. When the condition of light are very intense, so the PS2 unit are separated. They you know, they don't stack all together because the light is enough for, you know, this transformation. When the light intensity are very weak, so they can merge together in order to organize a cooperative action in order to store. So these are, you know, the imaging of the core shell unit where we have the reaction center here surrounded by the antenna, okay? This concept, okay, is, and here you can see an enlarged version of it, okay? So this concept is the concept of, quantasome, okay? So an integrated unit that can transform quanta of light. And this was the very first concept of biologists that were actually describing, you know, these photosystems that work with with many antennas, okay, and that surround the reaction center. This is important because we have to concentrate light, okay, because we are dealing with a very difficult process, okay? So in the artificial environment, so in our lab, how can we design a quantasome version of this kind of natural system? Well, we teamed up with Maurizio Prato in Biomagune in San Sebastian, and so we were reasoning, okay, that we have a catalyst for water oxidation. I will introduce it just in the next slide, and we need to organize this kind of shape. So, a corolla of antennas that feed, you know, the catalyst with a cooperative action, okay? And this is the catalyst. This is a polyoxometallate, okay? And we synthesized this in the early 2008 years, and you can see in the very center of this molecule, this is a molecule, is a big one, because it has a 2 nanometer dimension, the longest, with a 1 nanometer, you know, size in the shorter dimension. And it has 2 kgs of tungsten oxide in order to stabilize a reactive ruthenium oxide core, okay? Water oxidation occurs here at the core of this catalyst, okay? So if we look at this catalyst, okay, we may see that this is, you know, bridging the gap between the natural polyoxometallate made of manganese, okay, and what is the best catalyst for electrolyzers in commercial electrolyzer, which is the ruthenium oxide. What is the advantage here? That we have isolate a tetraruthenate core that is, the smallest unit enabling water oxidation with a very low overpotential. Okay, so we reduce the content of ruthenium that we apply. Why not manganese? Of course, we are working on manganese, but manganese is not stable during the reaction turnover. It's not stable even in the leaf. Okay, the leaf needs to reconstruct the oxygen evolution center every half an hour. And this means that we are losing energy, okay? And indeed, the efficiency in the solar conversion of the natural photosynthesis is very low. Part of the loss is due to the continuous and perpetual reconstruction of very fragile structures, okay? So, anyway, we then reasoned about what kind of antennas and molecules. Okay, yes. How do we know this? I mean, this is electrochemistry, so the ruthenate core can, of course, evolve oxygen. We can see, we have 4 electron transfer processes that occur before oxygen evolution. So this is, the mechanism is really close to the natural mechanism, okay? Okay, and but the interest and the overpotential is very low, and it matches the one with of the natural system. Okay, so we need to engineer the antennas that surround the oxygen evolving center, and the way we can do this, okay, is to engineer this antenna that upon light excitation evolves in a very strong oxidant, okay, that can extract electrons from the catalyst and from water, and in this case, evolving oxygen, okay? So which kind of antenna we can use? Okay, here it is, okay? So we need some features of our antennas because we need to generate a very strong photooxidant. So we have to go beyond 2.2 volt in order to drive this reaction, because the ligand of water are very stable, okay? And so we turned our attention to this kind of molecules. These are the relins, okay? These are also defined as the smallest, most atom-efficient chlorophyll mimic, because you can synthesize this antenna, covering all the photosynthetic visible range. And what we did, indeed, okay, we turned our attention to this molecule, which is a perilene bis imide, okay? It has an aromatic core, and you see, it's functionalized with 2 positive charge at the very periphery of this molecule, and this is because we need a positive charge in order to organize this antenna around the polyoxometallate. The polyoxometallate is polyanionic, so if we manage to have a geometry, a core shell geometry, and we manage to generate a very, the photooxidant from the perilene bis imide, we will have, the 4 electron mechanism and 4 proton that we need, and at the very end, we will evolve oxygen, okay? So how we did that? Okay, how we are sure what is the structure that at the very end we were able to do. Okay, so if you put this molecule in water, of course they aggregate because they are very hydrophobic. And usually perilene bis imide are a semiconductor that organize in this kind of rods, okay? But when you put them in contact with the polyoxometallate exfoliates the perilene bis imide's rods and makes this kind of 5-to-1 complex, okay, and we have characterized this by spectroscopic and by, electrochemistry, spectroelectrochemistry, and conductimetric titration, but I cannot show you. Okay, here we go. But most important, by small angle X-ray scattering. So what we have in solution is the formation of this unit. This is a 5-to-1 unit because we have a neutralization of the charge. But what happens is that, we have an hydrophilic core that is surrounded by hydrophobic walls. And in water, you have a hierarchical aggregation forming lamellae, and you can see this by small angle X-ray scattering. And then, you can also have a hierarchical formation of these stacked lamellae, okay? And this is important for our system because it's really reminding the structure of the chloroplast membrane, okay? That they need this stacked form, okay? Because they collect more light. And this is a very new result, is a TEM, cryo-TEM image of our structure that we now can define a quantasm, okay? And you see, you have these hexagonal particles because this is consistent with this, a close packing of the unit in an hexagonal way, and you have these fringes, okay, that are consistent with this kind of stacking lamellae, okay? And in this kind of arrangement, we have, okay, yes, this is also the high resolution TEM, where you can see, the polyoxomedallate that is really surrounded by the perilene bisimides antenna. And in this kind of arrangement, of course, we have a high concentration of the exciton density close to the catalytic core, right? And when we put this, we build a photoanode, and so this is the material that is simply stacked on the tungsten oxide photoelectrode. We have oxygen evolution. This is the photocurrent for oxygen evolution. The Faraday field is quantitative, and moreover, the conversion efficiency reaches the 1.3%, which may seem very low, but this is one of the first examples with green photons, okay, in our and compared to the benchmark in the literature, okay? So how we can improve this? This I will be very, very fast, but you can sure understand that we have to improve the water solubility and the water access, and we have managed to functionalize the perilene antennas with this polyethylene glycol unit in order to create water channels. With these water channels, the photocurrent is really improved. Okay, this is the work of this magic team, and what I can also say is that, of course, the interaction of these quantasm units with polymers, can offer very great opportunities. Okay, we have described this in these journals. Okay, and also. If you're interested in this review, you will see, the artificial catalyst system or photo system compared to the natural one, okay? We have this green wall that it's really difficult to overarch, okay? And so, of course, our goal is to use low energy photon in order to drive this reaction. Okay, I think I'm done because I hate also this. Yes, of course, as you will see, we have ruthenium, and we are working for other oxygen cluster that can substitute the ruthenium atom, and of course we are. I have to thank all the collaborators. that I cannot show you now, but I mean, as you understand, this is a very interdisciplinary project, and so we actually work in collaboration with all these partners, and this work is included in a Pathfinder project called Plankton. Thank you very much for your attention.
Thank you very much, Marcella, for this excellent talk. I think we have time for one question. Is there one question? I don't see a question. Maybe it's a chance for me to ask a question. You have shown these very nice TEM images of the membrane structure. Is there a certain risk that the electrons in the TEM destroy the structure, or how you are handling this?
No, I mean, we actually, this was our attempt to use TEM in order to have the imaging of the core shell hybrids, but all our attempts were actually destroying the organic part, because this is a supramolecular complex, okay? So now that we can, link the unit with the polymers, okay? And of course, we use cryo-TEM conditions, we manage to have the images of the fringes, which is good. Thank you very much.
Good, thank you for this explanation. So thank you very much again. Our second speaker is Elvira Fortunato. She is professor at Nova School of Science and Technology here in Lisbon, in Portugal, and it's the only scientist I know who got 3 ERC grants. So, Elvira, we are looking forward to your talk.
So, good afternoon. It is a real pleasure for me to be here and to present you some of the work that we are doing at CENIMAT I3N, and I will talk a little bit about materials and also technologies that are sustainable, especially to be used in electronics. So concerning the outline, I will start just with a briefly introduction, showing a little bit about the problem and also part of the solution. And after that, I will present you some of the work that we have done within our laboratory, CENIMAT I3N at Nova University. And after that, some final remarks. As you know, we are facing today a huge problem concerning to electronic waste. And for example, in this graphic on your right, you can see how the amount of electronic waste we are producing. And for example, in 2022, we produced 62 million tons of electronic waste, and if we keep with the same rate, it is expected to reach by 2030 82 million of tons. So this is not a good way, and also this is not the best way to recycle all these electronic waste that we are producing. So, of course, part of the reason is related to the world population. We are now almost 8 billion persons, and also the tendency is to increase. And we are using much electronic components, basically mobile phones, televisions, and also computers. And part of the solution that I would like to show you today is related to sustainability. And for example, here we have what we used to say the wheel for sustainable electronics, and we must start within the design of the products that we want to produce. So we must start with the eco-design. After that, we must carefully choose the sustainable raw materials, and also some, if possible, some biodegradable materials in terms of the materials. And after that, since we need to process the materials, also we need to choose sustainable technologies. And at the end, the products that we are developed must be recyclable. So we need to follow this wheel for sustainable electronics. So now I will talk a little bit about the materials and why we start to work with cellulose inside our laboratory. And as you know, cellulose is the most abundant biopolymer, is flexible and unbreakable, is a low-cost material, is the lightest known material, and for some specific applications, this is a huge advantage. Is the technology for producing paper is very well established. For example, here in Portugal, within one of the biggest companies in Europe, Navigator, we are producing paper, office paper, at a velocity of 100 kilometers per hour. Cellulose presents very good dielectric properties. Paper is ubiquitous. It means that we have access to cellulose or to paper everywhere in rich and poor countries, and at the end is recyclable. So for example, if we take a look at how cellulose is extracted, or how we extract cellulose, as you know, cellulose is extracted from the wood, from a pinus or eucalyptus trees. But in that case, this vegetal cellulose, we need to wait almost 10 years just for the tree to grow, and after that to extract cellulose. But also as an alternative, if we have a specific culture of vinegar has inside some bacteria, and also we are able to produce cellulose, in that case nanocellulose, produced by the acetobacter. So here in this image from on your left, we have a scanning electron image with a bacteria, this green microorganism, and these bacteria, they work like a nano extruder. So they are in function of the culture, they are extruding these fibers of cellulose, but since the diameter is so small, is of the order of nanometers, we used to say, or we call these cellulose nanocellulose. And in fact, since the fibers are at the nanoscale, we don't have interaction with the visible light with this material, and these membranes, the membranes produced by these bacteria, they are transparent, as you can see in this image. And again, for example, if we compare the vegetal cellulose with the bacterial cellulose, in these two images from scanning electron microscope, on the left we have cellulose coming, vegetal cellulose, and as you can see, and on the right we have the nanofibers, cellulose with origin on the bacteria. But if you take a look on these figures, they are quite similar. We have a 3D random orientation of these fibers. The only difference, or the mainly difference, is related to the scale. On the left, we have 100 micrometers, and on the right, we have 100 nanometers. So, and also if we take a look about these membranes produced by bacteria, these bacteria, we can see that we have a stacked structure, and we are able even to say that this is one of the first 3D printing by nature. Also in the previous talks, we scientists, we are inspired by nature, and again, nature is inspiring us, and also nature is already producing 3D printing, in this case, nanocellulose. So now some examples about some devices that we have done at our laboratory. So in 2008, some years ago, we started to work on green electronics. As you remember, in 2015, the United Nations launched the 17 Sustainable Objective Goals. But much before 2015, in our laboratory, sustainability was already a key issue. So in 2008, we developed the first paper transistor. As you know, we are surrounding nowadays with e-papers, e-journals. So the idea is to have, instead of journals, we are substituting journals, newspaper, by some electronic components. But in our case, we want to use cellulose as a truly electronic material. And this is why we moved the E from left to right, and instead of working with e-paper, we are working on Paper-E, and we registered this brand, the Paper-E, and the logo is Green Electronics for the Future. So indeed, this was the first paper transistors we have done in our laboratory. So we are just using cellulose as the dielectric component for the transistor. This is a very easy thin film effect transistor, field effect transistor, and as semiconductor and also as gate, also we are using metal oxide. So all the components that we are using for these electronics are green, are recyclable. And again, some years later, we developed the same, using the same architecture, we developed the same transistor, but instead of using cellulose coming from the trees, vegetal cellulose, also we use these bacterial cellulose, and also the electrical performances of the transistor are much better, since we are the surface, the roughness of the material is much lower, and also the purity is much higher. So after that, we developed a lot of different applications. We have been involved in several national European projects, developing a lot of electronic systems. And after that, it was launched 4 years ago, a collaborative laboratory, Alma Science, that his role is developing all the products, or part of the products that we developed inside the CENIMAT I3N, and they want to exploit these applications for real applications and in a close collaboration with the industry. So besides the electronic parts, we start to work also on biosensors using paper. And this is a little bit followed by some guidelines or some advices by the World Health Organization. So they are asking us for affordable, sensitive, specific, user-friendly, rapid and robust, equipment-free, and also delivered in those in need for rapid diagnostic tests. So, and also besides that, if we take a look about the biosensor market, we have here some numbers. And for example, in 2021, the share was around 25 billions of US dollars, and it is projected by 2030 to more or less to double this value. So there is a need, and also there is a huge growing in terms of biosensors, and of course the cost of the biosensors must be reduced. Again, for example, if we take a look more precisely on some specific, on the biosensors market, you can see that the share will be between wearable sensors, the segment for wearable sensors, and also the point-of-care testing segments. We start also some years ago to work on colorimetric sensors. So this is a very easy paper-based device for glucose sensing. So this is a colorimetric sensor. We don't need to use an electronic equipment to read what is the concentration of glucose. We just developed an application for a mobile phone, and function of the color, we are able to see, to measure what is the amount of glucose. We also have other applications for these biosensors, not only for these colorimetric sensors, but also even for COVID and also for other virus and bacteria. So we are working a lot in this direction. So besides this, the material that I present you on, based on cellulose, as I mentioned at the beginning, and remember the wheel for sustainable electronics, besides the materials also we have the technologies. And I want to introduce you a new technology which is called laser-induced graphene. So this is invented in 2014 by Professor James Tour in Rice University, and also as on the right you can see after that discovery the number of papers that start to appear related to this new technology. And of course this is quite important because this laser-induced technology or direct laser writing, because it's not only able to produce graphene, also you can use these laser technologies for developing and for synthesizing other materials, has a huge impact on biomedical engineering, also on flexible energy storage mainly also some microcapacitors. And for example, if we take a look on the wearable biomedical applications, we can use or we can exploit this technology for a large variety of sensors, starting from cardiovascular sensors to glucose, blood oxygen, blood pressure, and so on. So this is very easy. So we can, by choosing the appropriate precursors that we want to transform on graphene, we can start with some polymers. Also, we can use cork or even some or cellulose. And by carefully choosing these type of precursors and using also and by optimizing the laser parameters, either if we are able to use infrared laser or even a ultraviolet laser, we are able to transform the surface of these materials into a graphene layer. So this is quite powerful because it's a mask-free production. We don't need to go to inside the clean room to use masks or lithography. We just write the pattern that we want. It's a single step, is energy efficient, is fast, is scalable, which is quite important if you want to translate this to industry, and at the end is a low-cost process. So here on these yellow boxes you can see the properties. So I would like to highlight the high specific area, because especially if you are looking for, we want to use this on biosensors and we are using liquids, the surface area is quite important. And also in terms of the electrical resistivity, we can achieve the values as low as 5 ohms per square. So here are some examples. We start with some UV sensors using these polyamide substrates transformed into graphene, and after that by using also a very easy technique for the zinc oxide nanoparticles, we are able to produce some UV sensors. Also, we produce the same type of sensors using cellulose nanocrystals. It was also a joint collaboration with a PhD student from Brazil. Also, we developed some strain mechanical sensors, for example, for arterial pressure, wave monitoring. Also on the right, also pressure sensors for to be used in smart cork easels for gate analysis. Also some more strain sensors for example, for detecting electrophysiological parameters from the human body. And also here it's quite interesting because we are just using office paper, and we induce the graphene layer on top of the paper, and after that, as a tattoo, we detach the graphene layer to another membrane, to a very thin membrane, in order to be able to have a very high resolution pressure sensor that we can use and we can touch in our skin. So here are more examples. Beside the biosensors we developed, we work on energy, and here are some examples of micro supercapacitors, also using paper or using cork. We are able to produce this type of devices. And also within these energy devices, this is an example where by using only a single step, we are able to induce the graphene layer on top of the paper, and besides that also we synthesize some metal oxides simultaneously. So this process is not only used to produce the graphene, but also to synthesize the metal oxides that we want to use. Also, we perform some electrochemical biosensors for glucose, here either enzymatic or non-enzymatic ones. And more recently also we are working on some systems. We integrate into one single device, electrochemical sensor, and also with a technique to induce sweat, and we are able to analyze the glucose not from the blood but from the sweat, and this is quite easy. more electrochemical disposable pH sensors. Also on the right you can see how they work quite well. And as final remarks, I would like to stress that remember, in terms of sustainability, we must look for sustainable materials, and besides the materials, also we need to look for sustainable technologies. So this is the main message that I would like to present you, and also I would like to thank our group, that part of them are present here, and I thank you for all the work that you have been doing over the years. And not only to the persons, but also important is the budget and the financements that we are getting. So we are quite proud that we succeed in having a lot of European research grants. I got 2 advanced grants and 1 proof of concept, and besides European money, we have also support from national funds, especially FCT, and nowadays the PRR from Repower EU. So thank you very much for your attention.
Thank you very much, Elvira, for this very nice and very, from the deductive point of view, also very nice talk. Are there any questions?
Question concerning your laser technology. Is it possible to get graphene with different crystallinity? Because, as you know, pure graphene crystal may be either insulator or conducting species. So is it possible to play on these?
Yes, it is possible, and also depending on all the deposition, all the conditions that we are using, and also on the types of lasers. If it is infrared or ultraviolet, it is possible to change the properties of the graphene layer that we are producing. Nevertheless, for this case, we are targeting high conducting graphene, because this is what we are looking for. But also, for example, for synthesizing other materials like metal oxide, zinc oxide, also other metal oxides, it is possible to adjust the electrical properties.
Are there other questions? Yeah, please.
Do you see the same graphene that you will be generating? For example, I saw you do the polyimide, for example, on cellulose. Is this the same material, or it's what are you looking for? Best conductivity, and is it the same material will be, and different substrates?
Depends. It's not exactly the same material, because also the composition, especially the chemical composition of the precursor that you are using, is different from a cellulose or, for example, from polyamide. But at the end, what we are targeting at this moment is to achieve a high conductivity, but besides that, also we are controlling the morphology of the graphene layer. Because depending on the process, on the laser parameters, you can have a more porous or less porous structure. So that there is a balance.
Be more important in the biosensing, right?
Yes, of course.
There's another question.
It's possible to repeat the first part of the question.
I want to congratulate you.
Thank you.
It's fantastic. And I was wondering about the durability of the device, and depending on that, if you have think on using as an oximeter, because the ones that we have nowadays, they do not work the way we wanted, really. They are around the amount of oxygen that's in the blood. Thank you so much.
Yes, thank you. Not at this moment, we are not working precisely in this specific sensor, on oxygen pressure sensor, but we are working a lot on wearable. And the idea is for the wearable devices, instead of using a single device, we want to integrate different devices in the same wearable system. And in that case, even if the blood pressure or the oxygen concentration is not exactly the best values, the combination sometimes is much better for a clinical point of view. So this is the strategy, to integrate.
Are there more questions? I have one question, very general question. You have this laser-induced graphene that you are manufacturing. Could you imagine that there's also electron-induced graphene, and to make the structures even smaller? To use an electron beam instead of laser?
Yes. This was already done, not in my laboratory, but in Tour laboratory, yes. It is possible, yes. And in that case, the resolution is much higher.
Yeah.
This is why now also we are working with the ultraviolet laser, because the wavelength is smaller, so we can induce smaller structures. But this was already done inside the microscope.
Okay. Thank you very much. Let's thank Elvira again. Okay. So the third speaker will be Jose Maria de Teresa from the Institute of Nanoscience and Materials from the University of Zaragoza in Spain.
Thank you, Mr. Chairman. It's a great honor to be a new member of the Academy and to give a talk in this historic building. So I will show some work we have carried out at the Institute of Nanoscience and Materials in Zaragoza, in the north of Spain. We have two collaborators from Germany, one from Frankfurt and another one from Dresden. So the topic is the use of spin-coated organometallic films that we decomposed with focused ion beam irradiation. So we used two different equipment to do this focused ion beam irradiation. One of them is this dual beam system, in which we combine a scanning electron microscope and a gallium focused ion beam. And the second type of microscope is this helium ion microscope, in which we can combine helium or neon ion sources with gallium focused ion beam sources. You want to get more information about our work, you can visit my webpage or write an email or follow me on Twitter, or if you can understand Spanish, you can follow my podcast where I interview other scientists, Conciencia. So let's put my research in context. Let me recall you that microchip technology nowadays is based on silicon wafers. Microchips are fabricated on these silicon platforms, and the main ingredient, the main device is this transistor, where you have a source of electrons, a drain of electrons. You have the current through the active channel, and you can modulate the current through this channel through the gate. So you can switch off or on this transistor and allow the current flow or being stopped. Thanks to this technology, Gordon Moore, the founder of Intel, proposed that using lithography techniques, it could be possible to double the number of transistors per a given area every 1.5 or 2 years. This has been true, and in fact, nowadays we have 100 million transistors per square millimeter. So for that, we need to do fabrication inside a clean room, and current technology relies on extreme ultraviolet lithography techniques. So production is mainly carried out in Asia, but the machine to do this EUV technology is manufactured here in Europe, in the Netherlands, by the company ASML. This is a complex machine, and I would like to comment two key ingredients in this technology. One is how it works. You have to produce wavelengths in 13.5 nanometers. You have to produce photons in 13.5 nanometers wavelength. And for that, you have some thin droplets that you have to melt and vaporize with a laser. And then you create a plasma that emits photons in this wavelength. So here you produce these photons that are driven through mirrors to a reflective mask. And then the patterns in this mask are projected on the resist that covers your silicon wafer. This is the way the microchips are fabricated. But focused electron and ion beam technologies are key in two steps of the process. First, for mask repair, because it's not possible to fabricate these masks without defects. So they have to repair these defects. So for example, here you see one defect in this mask, so the pattern has been removed effectively. So you can repair it because using focused electron and ion beam technologies, you can remove material and you can grow material at the nanoscale. So you can rebuild this mask. In a second process, you can do circuit editing. This is key because in the prototyping phase of microchips, there are also some defects, and these microchips have to be reconfigured. For that, you have to drill holes. For that, you can use the focused ion beam, and you have to grow to reconfigure the connection, the electrical connections. So for that, you need to grow material at the nanoscale, and you use, again, this focused electron and ion beam technology. So I have a video animation to show how it works. So you can see here the focused ion beam. This is similar to a scanning electron microscope. You have, in this case, a gallium ion source, or it can be a helium ion source. And then you can scan this ion beam on the surface and create a hole in the structure. This is called focused ion beam milling. But if you insert a gas injection system, you can inject a gas that is decomposed by the ion beam, and you can grow material. This is a nanowire grown in the plane of the substrate, and you can use it, for example, to produce electrical contacts at the nanoscale. So in this way, you can measure the electrical properties of individual structures such as this one. Interestingly, you can also grow three-dimensional structures. So this is the growth of a pillar, but if you give the ion beam this circular shape, then you can grow, for example, nanohelices. Also, it's interesting that you can do this nanolithography on any substrate, not only on flat substrate as other lithography techniques. And you can modify, for example, the tip of an atomic force microscope. Okay, what is the problem with these direct write techniques called focused electron beam induced deposition or focused ion beam induced deposition? That the charge dose that you need is very high. I will use in my talk the term charge dose or fluence, meaning the same. It's measured in microcoulomb per square centimeter. And you see that these direct write techniques need a lot of charge. So this means that these processes are very slow. So you can compare with standard lithography techniques at the nanoscale, such as electron beam lithography, that require electron doses between 100 and 1,000 microcoulomb per square centimeter. In Zaragoza, we have been working in the last years in developing new nanolithography techniques to improve the throughput, to require or processes that require less charge dose, so they will be much faster. I don't have time to discuss one of them, cryogenic focused ion beam induced deposition. Today, I will only discuss spin-coated organometallic films that we decomposed by focused ion beam irradiation. So, in fact, this is not a new idea. It was already proposed in the 80s in Bell Labs. But there was a big disadvantage, as you will see now. So it's what proposed in '86 that using these organometallic films, if you decompose it with the focused, at that time, micro-focused ion beams, you just need to develop in a certain solvent, and directly you create a metallic structure. So it was a direct patterning of metals, and you provide the functional material without the need of sacrificial resist, but there was a disadvantage, that you needed a post-processing annealing step. You needed high temperatures, high aggressive atmospheres to do this process. So the idea somehow was abandoned because there were other techniques developed, such as electron beam lithography. Other people tried to use electron beams to decompose these organometallic films, but they had the same problem. They needed these annealing steps. So we decided to explore this idea with modern focused ion beam systems to avoid the need of post-processing step. And we were successful. So we used palladium acetate films that we create on a substrate by simple technique, spin coating. Then we do the ion beam irradiation. We can freely design the pattern. And then we just need to remove the non-exposed material by immersion in chloroform. So in a very fast way, because the charge dose that you need is very low, as you will see in the next slide, we can produce metallic structures based on palladium in a very simple way, and without the need of any post-processing. So here we have more details of the process. We create these structures that are suitable to measure electrical properties. So this is the palladium acetate precursor. This is the focused ion beam irradiation. These are the conditions, 30 kilovolt, ion beam carriers between 1 and 24 picoampere. And what is interesting, the area dose, the charge dose that you need is very low, between 2 and 100 microcoulomb per square centimeter. And then we remove the non-exposed areas by using chloroform solvent. Okay, so you can see here the summary of the result. The resistivity is measured as a function of the charge dose used. And you see that above a dose of 20 microcoulomb per square centimeter, we reach a very low resistivity of 75 microohm centimeter. And we can do the processing with very high resolution. Here, we have a resolution of 40 nanometers. You see the irradiation area is large, 146 square microns, but we only need a few seconds of irradiation. If you try to do this with direct write techniques, you will need a few hours. So what is the explanation of this low resistivity? When we do cross-sectional transmission electron microscopy, we observe that we produce palladium-rich films in which we create these palladium grains that percolate and allow the conduction of electricity. The palladium content in the optimized dose is 60 atomic percent. We have tried several ions. Yeah, so apart from gallium, we have tried neon irradiation, helium irradiation, and electron irradiation. And here you can see that the lowest fluence is obtained for gallium and the lowest resistivity. So the optimization is produced by the fact that we have the largest palladium content, almost 60%. So what applications have we explored with this technique? For example, we have done electrical contacts on nanowires. Here in orange color, we have a nanowire, and we have put 4 electrical contents. The irradiation area is very large, is more than 500 square microns, but the irradiation time is only 7 seconds because we are using 24 picoampere current. We have also explored the creation of large area conductive meshes that can be interesting to provide electrical conduction to insulating substrate. This can be interesting in optoelectronics applications, where normally you have insulating materials, unless you use materials such as ITO. Here we produce these small structures that do not stop light from going through the material, but they produce electrical conductivity, as we have measured with current versus voltage measurements. And the last application I want to discuss is the gating of superconducting nanowires. So superconducting nanowires are being studied for high-frequency electronics. And if you use conventional electron beam lithography, you can prepare this kind of structure. Here in blue is a superconducting nanowire, and here you have two gate contacts produced by electron beam lithography. And what you observe is that when you apply this lateral gating, you can switch off the superconductivity. So when you measure resistance versus current, below the critical current, the resistance is 0 because the nanowire is superconducting, but when you apply the gate voltage, then you suppress superconductivity and the nanowire becomes normal and you have a normal resistance. So we have done the same kind of gating using our technique, organometallic films that we decompose with the ion beams. So we produce this kind of structures based on palladium, where we can apply this lateral gating. And also we have explored top gating. For top gating is more difficult, is similar to a field effect transistor. So here you need a dielectric covering the superconducting nanowire and then the conductive top layer. Yeah, so in the lateral gating, we obtain similar results to those obtained when we do the patterning with electron beam lithography. So the material, the nanowire, is superconducting when without application of gate bias, but when we apply the gate voltage, then we switch off superconductivity and we obtain the normal resistance of the nanowire. So this is how we do it. First, we use our organometallic film that we decompose with the focus ion beam. Then we grow the superconducting nanowire. You can see here the dimensions. And then we apply this lateral gating. For the top gating, it's more complicated. We have, for the dielectric, we have used electron irradiation. Because if you use certain fluence, you can get a very high resistivity. So this works as a dielectric material. And for the metallic part, we use the standard conductive material that we produce with gallium focused ion irradiation. So these are the steps of the process. First, here we grow the superconducting nanowire. And then first we create the dielectric layer with focused electron beam irradiation. We use two different layers in order to have a thicker dielectric layer. And then using gallium focused ion beam, we produce the metallic contacts. And again, we can observe that as we apply the gate voltage, we switch off superconductivity in the nanowire. Here is the transmission electron microscopy image where we can see the different layers, the dielectric layers and the conductive layer. And this is my last slide. This is the summary. I hope I have convinced you that the use of focused ion and electron beam irradiation of palladium acetate organometallic films is very efficient in order to directly fabricate electrical contacts and electrical gates. And we are now exploring other organometallic films and other applications. These are our funders, and thank you very much for your attention.
Thank you very much for this very interesting talk. Are there any questions?
Thank you very much for your Interesting talk. It is possible to scale up this technology for large area fabrication for microcircuits?
Yeah, so the first answer is that the technology is faster than electron beam lithography. So now we know that there are many devices that are produced by electron beam lithography. So in that sense, is comparable to the speed of electron beam lithography. And also, you can use also broad beams combined with masks, with physical masks. And in that case, you can also work at the wafer level. This would be another step.
Thank you.
You're welcome.
I have a question connected to this one. If you are saying it's faster than electron beam lithography, is this also true if you are using helium or neon?
No, in that case, no, because you need larger charge dose. With helium and neon irradiation, you can gain in resolution. But you need, yeah, so if we have a look, okay. Yeah, on the slide in which I compare all the ions, you can see that you need maybe 2 orders of magnitude larger dose. So in that case, it's a bit higher than in the case of electron beam lithography.
Okay, thank you. Is there one additional question? No, then let's thank the speaker again.